Vsepar theory, part 1, predicting shapes of molecules. Okay, what we are going to do is we are going to try to draw the best Lewis dot structure that we can, and then we're going to try to name it and draw it. Okay? And it's, so just by drawing a Lewis dot structure, you can actually predict the shape of something as tiny as a molecule, right? It's crazy. So I'm going to ask you some shapes of things, and the answers are really right here. But it'll really help in drawing these things if in your mind you can picture what you're trying to draw, this three-dimensional shape. So if you're like me and you can't really draw very well, at least you still have the picture in your head. It'll help you get and predict the right answers. It really will. So see if you can put some energy into seeing these shapes. Okay. So we're going to talk about total a lot. We have the total valence electrons. That's not the total I'm talking about. I'm talking about the total number of things surrounding that center atom. And here, this is the center atom's always the purple guy in the middle. So I've got 2 atoms surrounding it. And for all this naming to work, the surrounding atoms have to be identical. Okay. So this shape is linear. Okay. I'm going to add an atom on there. Okay. What do they call this shape? Trigonal planar. It's a flat triangle, right? It's a flat triangle. Add another one. And they call this what? Tetrahedral. Now notice, this is what's important to realize, is that it's got a triangle for a base, right? And then you have one in the center, then you have this guy coming up. If this one was gone, you'd still have a pyramid, kind of, with a triangle in the base, right? So that's 1, 2, 3, 4. So if you would draw a Lewis dot structure with 4 surrounding atoms, they're all identical, and no lone pairs, this is what you'd have to draw. Okay, and we'll show you how to draw it, but that's 4, 5 surrounding atoms, right? Now notice you still have this triangle in the middle. I can rotate it there, right? 1, 2, 3, triangle in the middle. It's symmetric. There it is. Here's a triangle in the middle, and top and bottom. So they call this Trigonal Bipyramidal. And the bi meaning because there's 2 pyramids, right? Here's a pyramid on top, and there's a pyramid on the bottom. Okay. Our last one. Okay, now you've got a square in the middle, right? You have a square in the middle, the top and the bottom. They call this octahedral. I kind of like the name better, square bipyramidal, because that's what it. Octahedral. You think of 8. Well, it does have 8. It has 8 sides, but I don't see anything to do with 8 here. I like the name square bipyramidal better, but you can call it. You can call it either one. Okay. So, let's see here. So I've been saying Vsepar, but Oscar, what the heck is Vsepar? Do you know what it stands for?
Oh, valence.
Valence. Shell. Anybody else know? Oh, good. Valence shell, electron, pair, repulsion. I don't know, it doesn't really matter you know the name or not, but that's what it stands for. Valence shell, electron, pair, repulsion theory. The reason why I go over it is because the idea of this, let's say we have our flat triangle. So this is if you draw a Lewis dot structure with 3 surrounding atoms, no lone pairs. But what if you had a Lewis dot structure with 2 atoms, surrounding atoms, and 1 lone pair? I'll remove one, put a lone pair on there. That's the idea of, this is the idea of the Vsepar, valence shell, electron pair, repulsion. It takes up a lot of space, these electron pairs. They just repulse and push everything out of the way. And that's what really creates the shape of these molecules. These lone pairs just push everything around. Okay. But if you don't have any lone pairs, right, it's trigonal planar. If you do have a lone pair, it's not trigonal planar anymore. Because you can't see the lone pairs, the molecular shape, all you can see are the atoms. So now the shape would be bent. And that's the road we're going down. So let's go ahead and put in, well, first we know that if you have the total, let's fill in this table here. The total is the number of surrounding atoms plus the number of lone pairs, right? And what's a lone pair? Remember, that's a lone pair of electrons. Okay, so the total number of things surrounding that center atom, right? It could be 2, 3, 4, 5, or 6. So in order to kind of mention the names, especially if there aren't any lone pairs, if we had 2, we called it linear. Then we had trigonal planar. And spelling counts. Then we had tetrahedral. Right? And then we, for 5 things surrounding, we had the triangle in the middle and the top and the bottom. We had 2 trigonal pyramids. So trigonal bipyramidal. Excellent. And then we have a square in the middle with a top and a bottom. You could call it square bipyramidal, or the book likes octahedral, so I'll give both. Octahedral or square bipyramidal. Okay, so how do we draw these three-dimensionally? What they want us to recognize is there's, let's kind of go up here somewhere. There's 3 directions, just like X, Y, Z. Right? And they're going to call this direction the plane of the paper, or in the paper. It's right that way. In the paper sounds better. So if you draw 3 directions of bonds, these are the bonds, right? So you're going to have one atom on each end, right? I don't know, X and X or something. But the point is, if you draw a solid line, that means that that bond is in the paper. If you draw a bond between 2 atoms that is dashed, not solid, dashed, that means that the bond is going straight back. From the paper, right? It's going straight back from what the paper is. So there's only one direction left now. You've got the plane of the paper, right? You've got going straight back. Well, then you have to have straight out. That'd be your 3 directions, X, Y, and Z. So out of the paper would be the last one. And this is where they draw that funky wedge. Right? So you'd have an atom, a bond like that. So that bond is going straight out of the paper, just sticking straight out. Okay, when you draw it that way.
The X should, I guess, you're that.
So, well, it'd just be sticking out. So you'd have one atom in the paper and one atom sticking way out here.
Oh, okay.
So my X's are just my atoms on the end of the bonds.
Oh.
That's all my X's are. You don't even really need to draw them if you don't want to. Because it looks better. Might look better without the X's. Get out of there. Get out of there. Whether you like to draw the atoms or not really doesn't matter. Okay. It will later on. Okay. So let's see if we can draw this stuff. So linear, right? So I think let's stick to that. Let's not draw in our atoms. Let's just draw the bonds, right? I think it's easier to see. So let's just leave the atoms out of there. Okay, so linear would just be like that. The center atom would be in the middle of the line of that. All right, and then you're going to have your surrounding atoms on the outside. Trigonal planar. The book likes to have stuff sticking out at you when they can. So, how should we? Let's draw one of each. One of each direction, maybe. Or since it's just a flat triangle, right, you can just draw all 3 the same. The book kind of likes the wedge one, but what we're trying to draw is this, bless you, right? Our flat triangle. So if you have a Lewis dot structure with, bless you, 3 surrounding atoms, no lone pairs, we need to draw one of these two. Okay. And the name is, what we already named it, Trigonal Planar. Tetrahedral, 4 things. The book likes to draw it so that you can see that triangle on the bottom. Right, here's your top, and see if you can draw that triangle base of a pyramid. Okay, so there's your top, and then you kind of see if you can draw that triangle of a base on the bottom. Okay, so that you can picture it. You have one going back, one going forward out of the paper, one in the plane of the paper. Right, so that would be this one. Right, 4 things. This one's going straight out at you. Plane of the paper, plane of the paper. This one's going back. Trigonal Bipyramidal. Now there's a little trick to this one. This one we're trying to draw this. And I think it's really helpful if you draw it this way. So you get this nice T. We're going to need that when we start adding lone pairs. See this nice T? Then we have one going back and one going forward. So draw that. We'll draw a T, and then we'll draw one going back, one going forward in the center. So we draw a T, and one going back, and one going forward. Okay. Then our octahedral, we need a square in the middle, and a top and a bottom. So you need a top, you need a bottom, and a square in the middle. 2 going back, and 2 going forward. Okay? So you would name the molecular shape octahedral, or square bipyramidal, if you had draw a dual Lewis dot structure, 6 identical atoms surrounding the center atom. No lone pairs. Okay, now what happens, you start putting in lone pairs. Okay. So if we go back, okay, add another one. So we have our flat triangle, trigonal planar. Add a lone pair, bent. So that's what we need to draw. So you pretty much just add a lone pair to our shape. Just pick one and add a lone pair. All right? Or just bent. That'd be bent. Right. And remember the names for everything we already did. Those are the names. We already have the names for those. Okay, bent. Can't add any more lone pairs. Tetrahedral. We add a lone pair. Okay, here's my tetrahedron. All right. I'm going to remove one, add a lone pair. Okay, I've got my, it's not a flat triangle, right? But what the base is, and they like the pyramid naming. Stick with the pyramid stuff. What type of pyramid is it? Triangle or square? Triangle. So it'd be trigonal pyramidal, not trigonal bipyramidal, because there's only one pyramid. So that's what we need to draw. So you pretty much just put a lone pair to the top, and then everything else stays exactly how you drew it for tetrahedral. Right? All I did is I just replaced that one. You put a lone pair on it. So that's trigonal pyramidal. And I can add one more lone pair. And then we should have our bent shape, right? So on our shape, we'll just add in one more. We'll have two lone pairs. And we have our bent shape. So it doesn't matter which one you remove it from. You'll end up with bent no matter what. Okay. And it's flat, so you could actually have two solid lines there that are bent, but that's okay. Trigonal Bipyramidal. Now this one is the only one I think that really has a trick to it. We're going to remove if we add lone pairs, add it in that order, right? So first we're going to add a lone pair to that back one. That's where we're going to replace it. So it would end up looking like you still have that T, and you have one going forward, and then you have your lone pair out here. It's gone. So what shape are you left with? Where is that? I grew up with this. I'm not so sure they're in the parking lot or in the playgrounds anymore. So here's trigonal bipyramidal. Here's my triangle middle. Just pop one off. We're going to pop off this back one. That was the order we're supposed to do it in. So now what's the shape? The only hint I can give you is this. Seesaw. You have one dude sitting on each end. Right? They call that seesaw. Okay. Now replace the second one. So we're left with pretty much this. That shape would be what letter? T. So they call it T shape. All right. Now remove the third. We have three lone pairs, so you'd have a total of 5. But if you only had 2 surrounding atoms and 3 lone pairs, you have to draw this. Remember those lone pairs, they just push everything out of the way. And that shape would be this is a straight line, so linear. Yeah, don't call it straight line. I would, yeah, whatever. Linear. Less words, I guess. Okay? So, all right. So remove one at a time. Let's see. There's my seesaw, right? Here's the legs, and here's a dude sitting here and a dude sitting here, going up and down, rocking, right? And then, whoop. There's my T shape with 2 lone pairs. Okay. I don't know if it would let me do that, but oh well, that's okay. So now the last one, octahedral or square bipyramidal. Add a lone pair. So we're just going to add it to the very top. All right, so we'll still have the 2 going back, still have the 2 going forward. So that shape would be square, what type of pyramid? Square pyramid, right? So square pyramidal, I guess, would be the best way to say it. Square pyramidal. Okay, and then you remove. Remember, which one would you remove next? The bottom one, because these electron pairs take up a lot of space. Okay, so we end up with just move the top and the bottom one. Big lone pair on top, big lone pair on the bottom. It's just flat square. We're not supposed to call it flat square. Square planar. Square planar. Okay. So the name of the game is pretty much use the questions will be like this. Use Vecifer's theory to determine the molecular shape of the molecule, right? And maybe draw it. So what I strongly suggest is, this looks like a lot, but dang, I really don't think it's that bad. Just know this one. I can make that thick, right? Just know this first column and draw it well. And it won't be so bad. Okay? Let's try it this way. Just know that first column, know how to draw them really well. Know how to draw Trigonal Bipyramidal. Right? Know how to draw Octahedral. Know how to draw each of these. And name them. Okay, let's try this. Try this first one together here. Water. It's a simple one, but it gets the point across. Get the valence first, because we have to draw the Lewis dot. Each hydrogen has 1. Oxygen has 6. So I've got 8 valence electrons. So you put oxygen in the middle, connect them. Anything left over goes on the center atom, right? So I need 2, 4, 6, 8. So my total number of things surrounding that center atom, the oxygen, is 1, 2, 3, 4, right? 2 atoms and 2 lone pairs. My total is 4. So this is what I'm strongly suggesting. Just draw the Lewis dot structure, figure out what the total is, and draw one thing. That one thing you memorized, the total for 4, and that's tetrahedral. And try to draw it really well. Try to draw it nice. In other words, draw it nicer than I draw it. Right? Because tetrahedral is trying to get it so that you have a triangle on the base and the guy pointing up, right? So it has 1, 2 lone pairs. So if you start here, you say, oh, okay, I have to add 2 lone pairs. So you go ahead and add them, right? Add one there. Pretty much you can add them anywhere here, but this is how we did it on our table. And then I'll end up having my hydrogen atoms here and here. Oxygen's in the middle. So my shape would just be bent, right? H would end up being bent. Okay? So when we go to the boards and work on this, draw the best Lewis structure you can. Figure out what the total is. The total number of atoms and lone pairs surrounding that center atom. Then just draw that one structure that you need to memorize. Right? That one structure right out of this first column. And then add the lone pair. Because usually if you draw it nice, you can kind of figure out where you're supposed to draw that lone pair and remember it. So let's try it. Here's a bunch. Determine the molecular shape and draw 3D representation. So we can go to the boards and we can help each other out. It's a Friday. Life is good. Right, Oscar? Yeah. Oh, because I counted up. The total is the number of surrounding atoms plus the number of lone pairs. So
surrounding atoms.
Yeah, so here's 1, 2, 3, 4 things.
Oh, okay.
So just count up everything that's surrounding that center atom. And a lone pair counts as 1.
Wait, a lone pair counts as 1?
Yeah. So even though there's 2 electrons there, remember it's a pair, so you're counting up the pairs. Okay. So ammonium. How many valence electrons? 8. That's your starting point. 8 valence electrons. Right? And when you draw it, so figure out what your total is, and then go from there. I think everyone's pretty much got it already. There aren't any lone pairs, so my total is 4. So you draw your nice tetrahedral shape and put an H everywhere. So make sure you put those H's on there, otherwise you get docked. And it has an overall plus charge, so make sure you put brackets and a plus on your ammonium 3D structure too. So yeah, so you need it wants the H's and it wants the overall plus. The only thing that you can leave out is really that nitrogen. You don't need to draw the center nitrogen, but you can if you want. I mean, if it helps you. I kind of lose the 3D perspective if I draw nitrogen in the middle, but. So if you got it, go on to phosphorus pentafluoride. Just be careful though, because if you have a lone pair, that's going to screw everything up.
Oh, okay.
Right? So be careful that you don't have any lone pairs.
Well, 8 times 5.
Yeah. So yeah, you're set. You're set. Just I want to make sure that you're checking it. Mm-hmm. Mm-hmm. So hopefully you're working with 40 valence electrons. So 5 times 8 is 40. So phosphorus has no lone pairs on it. So hopefully you found that your total is just 5, right? So that means you got to draw that T-shaped one. Don't forget to name. Oh, we forgot to name them. We got to be naming them. Like this one, we should have said tetrahedral. Forgot to do that. And spelling counts. Oh, bi is I, right? I can help you a lot more if you go to the boards because I can't see your work. Just sitting there. Make sure he's a dashed line.
Oh, this isn't.
Oh.
That was pretty.
Oh! Sorry. Okay. So hopefully you're working with 34 valence electrons on chlorine tetrafluoride ion. Mm-hmm.
So, trigonal bipyramidal, I got confused. It's the same thing as, well, not the shape, but it's named the same. Trigonal bipyramidal.
That's not bipyramidal, that's trigonal pyramidal.
Oh, trigonal.
That's only one pyramid.
Oh, that's the part.
So what'd you get for your total on that? Which one do you want? Yeah, so what'd you get for your total? Total.
Oh, what do you mean?
The total number of things surrounding that center atom. Whoa. But you also don't forget about counting your lone pairs. So 1, 2, 3, 4. You have 5 total.
Okay.
So draw the thing for 5. That's where I think you get messed up. Draw the thing for 5. Yeah, so but first I would draw the 3D structure for 5 total. And that's trigonal bipyramidal. Then put the lone pair on there. And hopefully if you draw it nice, you'll recognize where to put it. So do you remember, this is the one with the T, so you have to put them on in a certain order, so it's a lot easier to recognize. Remember which one to put it on, Jorge? Where do you put that lone pair on here? Because we need one lone pair on here. Put it on the dotted line. Put it on the dotted line. Because then, hopefully, you'll be able to see the little dudes sitting on the ends of the seesaw. Okay. Dude's just flying.
Is that right?
Man, you got the hang of this. Picked it up quick, dude. On D, 8, so let's see. Yeah, you do have a lone pair on that nitrogen. So the number of things surrounding that center atom is going to be 3 hydrogens and 1 lone pair. So my total is going to be 4. So draw the 3D shape for 4. The tetrahedral shape. Right, you try to draw it so you get that triangle base. Put our lone pair on there. Add our hydrogens. Yeah, I can't do math. You can, Alejandro. 34 valence electron. I couldn't add up to 34. But that's right. So sulfur tetrafluoride, hopefully you're working with 34 valence electrons. Right? If you get all the way to xenon difluoride, I think, Christian, you found it to be linear, right? So that's kind of an interesting one. This one, hopefully you'll find out that it's linear if you get that far. It's good practice. Alejandro, you found out that sulfur tetrafluoride was what? What was the molecular shape for sulfur tetrafluoride? You erased it, but what did you say? Seesaw.
Yeah, it was like.
The seesaw. Okay. See if you can get those. You have a few minutes left. Make sure you have a good handle on this. And again, draw the Lewis dot structure. Draw the best 3D shape you can for that total. Then add lone pairs if you need to. And hopefully the name will just stare at you if you draw it nice.
We just draw the F's.
Well, you have 22 valence, right? So you need a lot more lone pairs. Danielle, is this making sense? And don't forget to put the F's on there. They're going to want to see them. Nice. Now you need to put 3 lone pairs on. Yeah, there's 1. There's 2. There you go. Nice. See that? Very good. So you draw nice and neat like that? Should have had you drawn up here. It'll ease your pain and suffering. So have a good weekend.